Alright, so line of sight, curvature of the Earth. And first thing that came to mind for me was Columbus and the issue of whether the Earth is round or flat. And first off, higher frequencies and even light, and we won't talk about relativity at all, but they propagate in straight lines. And lower frequencies, like the citizens band, follow the curvature of the Earth. And you'll notice in the first picture, well, this picture, that the two antennas, they can see each other, they can communicate, there's nothing blocking it. But for the second one, these two objects can't see each other, they can't communicate, and that's why we have a satellite, so they can use it to send and receive transmissions. All right, so for this picture, it demonstrates a sand particle, the second one, a rain droplet. And E sub I is the incident electric field, and E sub S is the scattering electric field. And as electrons collide with sand particles, they scatter. And at higher frequencies, like the frequency we're using in Tanzania, scattering becomes more of an issue. Now, the gradient is a spatial change in temperature, pressure, or humidity. And with altitude, radio waves can be bent. And we have to remember that this is independent of the frequency. And also, weather, rain, sleet, hail, can also attenuate the radio waves and absorb some of the RF energy. Now, if the radio wave equals the critical angle, it can pass through mediums of different refractive indices, but if it's less than the critical angle, it will bounce back to the medium or reflect back to the medium that it originated in. And as you saw a few slides up, the antenna has to be a few wavelengths off the ground in order for the wave to propagate. And when Andrew and Jake were actually testing ours, they had them on huge PVC pipings and walked around like this. And one time they got on top of Hubbard Hall, on top of his car many times.
My name is Matt, or so we talked a lot about theory, the equation stuff behind the propagation. But one thing on a practical note, when you start to make applications sending radio waves, you can't just send out waves willy-nilly like this, because you're going to interfere with other things, with broadcasting equipment and other things. So each country allocates the different bands. And one issue we have is that because it's each country that has control of it, just because it's okay here, a certain frequency, doesn't mean it's okay in, say, Tanzania. So these are things, design issues you have to keep in mind. And the reason why they have these different bands, obviously, is because you don't want lots of interference. Everybody just can't be sending signals out, interfering, nobody would be able to get anywhere. I like to think of it as like roads. You know, everybody's not just driving around. We have public highways that everybody can use. There's private drives for certain people, you know, that only they can use, or there's restricted areas only for the government. So I like to think of it like that. Next slide. In the U.S., this is regulated by the FCC. You can see the testing and so you can see some of the different common bands: FM, AM, cell phone, even garage door openers, citizens band. Actually, it's a lot more complicated than this. Next slide. You can see here, this is all the different allocations in the U.S. Obviously, I'm not going to go through each one, but I want to show that is pretty complicated. There's red areas are for government only. There is a little bit area right here with satellite communication only government can use. Green is non-government, and black is both. And you can see there's lots of different allocations. So imagine that if each country has its own one of these tables, that can be very confusing. So we want to work to create standards. Next slide. This is done in the International Telecommunication Union. It's a specialized agency in the United Nations, and they work to create standards to bring this all together. Every country in the UN is a part of it, except maybe Pakistan, I think, is an observer, whatever that means. And this is represented by all these different languages. So, looks like this is their table for, you may recognize some of these abbreviations. These are different bands. Not very creative names, but they work. So we have high frequency here, very high, ultra high, super high, extremely high, and tremendously high. So it works, but you know, it's not very creative. Or if you don't like those names, you have the numbers on this side. So in summary, we talked about the electromagnetic fields and waves, Maxwell's equations, different mediums and how that affects the waves are propagating, how the electromagnetic waves propagate in the atmosphere, and the different standards and allocation. So Asante Sana, Rafiki. Asante Sana is thank you very much. Rafiki is friend. So any questions?
Okay, some questions from the class? Nothing? Okay, we'll go to mine then. You showed your antenna beam pattern, but you didn't really talk about the type of antenna you use. From that beam pattern, I can conclude it's a multi-element Yagi.
Yeah, I forgot to mention that, but it's an 11-element Yagi.
Okay.
Wavelength is about 70 centimeters. It's 433 megahertz.
Okay. And are you going to vertical polarize?
It's horizontal.
Horizontal?
Yeah.
Okay, why did you choose that over vertical?
One of the reasons is that the group last year, they already have, they actually have higher gain Yagis at the receiving end. So we're actually going to stack two Yagis on top of each other. If they're about half a wavelength in between the two Yagis that are stacked, it increases the gain by about 3 dB. So instead of having the 8 or 9 dB, just with one antenna, we'll have about 11 or so.
Okay. All right, and then I was glad you came back to 2 points. I had two other questions, but you eventually came back to them. One was the issue of sandstorms, because you listed glass as a great dielectric, sand is basically glass. Was that a problem last year? And
Not that we read or talked to them about. There is sand there, obviously, but it's mostly an issue for higher frequencies. It's still an issue for ours, but because the wavelength of ours is 70 centimeters, the wave is mostly a constant for a little sand particle.
Okay.
But if there were to be some sort of sandstorm,
yeah, sandstorms are really
Mhm.
difficult to transmit it because the sand basically clogs the air, and it's like having an insulator between two antennas. And then the other question I was going to ask was about the ITU. So Tanzania is a member of the ITU, so their frequency allocations should be pretty similar. I mean, if you look at that, there are some places that are areas that countries can assign, but by and large, you know,
The citizens band was different.
I'm sorry?
The citizen band was different.
Yeah, but that's a small little
Yeah,
slice
but
of the spectrum.
that's what we were testing here, but other than that, I
We're
think it
not
was pretty
around
similar.
433 megahertz, so we're in a VHF band, and they have that as a free band.
Yeah, it's unlicensed over there.
It's an unlicensed band over there. Okay. All right, very good. So that concludes all the technical presentations. Thank you.